Salam alaikum. Thank you for attending this presentation. For those of you who don't know me, my name is Adrian Pitts. I'm a professor of sustainable architecture at the University of Huddersfield in the UK. I've been attending conferences on comfort for many years now, and I hope I'm familiar to a few of the people in the audience. I was also fortunate enough to attend the first of the CATE conferences in Dubai a couple of years ago, which was a great event. I'm presenting this paper on behalf of myself and my colleague, Dr. Ring Gao, and the topic of the paper is overheating risks and impacts on occupant well-being in the COVID lockdown in UK apartment blocks. Quite a few different things there linked together, but with things which I think are very important to link together. I should also say that we've recently started a new research centre at the University of Huddersfield, which deals with sustainable living. So it's part of a whole area of research, which isn't just focused on the problems that are associated with overheating, but also some of the solutions. I think reason for being interested in this topic is the combination of the extreme of climate and the overloads from other factors. And I think that's often where we find most of the interesting research areas, is where we're combining together a number of different things, not just one area. So it's really interesting to see the range of papers, which are not just about overheating risk, but about some of the other areas. Anyway, I better start the presentation as a whole. I think we all agree that overheating and associated thermal stresses within buildings are increasing, and they're increasing at an alarming rate. A number of my students, even though we're in the UK, are interested in researching areas such as the Arabian Gulf area, looking at the extremes of climate. But we also have problems in more moderate climates such as the UK. And this is due to changing weather patterns as a result of global warming, and also because of some enhanced urban heat island effects. We're also finding there are increasing problems in using natural ventilation, which is the technique we would have traditionally used in the UK as a means of getting rid of the heat. And this is because of external air pollution and noise, and also because of the lack of controllability to some extent. What we're trying to present in this paper is an outline of research project that we've tried to quantify the additional problems and their causes exacerbated by the COVID precautionary measures. I think this really arises from the fact, although we've got various design techniques that can deal with overheating, when you add in the extra problems caused by COVID, this exacerbates the problems and can lead to very big difficulties. Even before the COVID pandemic concerns were being raised in the UK, there was a number of other groups working on the area of potential overheating risk. And it was pleasing to see the government had started some consultations on this. Unfortunately, I feel that maybe some of those differences, the improvements have stalled a little. And perhaps we're a little bit too cautious in the way we're dealing with this, hence why we instigated this project a year or so ago. Already in the UK, we do have a number of analytical methods for trying to assess the problem of overheating, such as Technical Memorandum 49 from the CIBSE, the Chartered Institute of Building Service Engineers, which considers design methodology for the assessment of overheating risk. But quite often the inputs to those overheating risk methods are based on a standard set of assumptions, which when you added in the effect of COVID, were not really valid anymore and might lead to some erroneous outcomes. So this is really why these assessment techniques, which were designed really for a different set of circumstances, run the risk of not dealing in circumstances where we have COVID as well. Now, the sorts of buildings where we were most concerned were in the apartment block type of building, the kind of building where it doesn't have to be a very large one, but one in which the place where a family might be located would be surrounded by other apartments, each of which would also be experiencing some kind of overheating. This, combined with the impact of perhaps single-sided ventilation and lack of air conditioning, which is very common in apartment blocks in the UK, would mean that there would be an increased risk of overheating in those apartments, and particularly when we add in some additional factors. So these areas are sort of summarized on the slide. That during the COVID-19 pandemic, the thermal heat stresses were exacerbated. First of all, because the government's first requirement was for people to stay at home. This meant everybody staying in an apartment for almost 24 hours a day. So isolating at home meant there were some additional difficulties. More members of the family likely to be in the home for much longer periods, 23 to 24 hours indeed. And this adding together with the additional heat gains that they would generate and the lack of availability of ventilation led to a number of different problems. Additional heat gains coming from more cooking, more use of appliances, and limited ability to cool the building from natural ventilation means, partly due to safety and security restrictions on openings. It's very common, in fact, for buildings in the UK that are apartment blocks to have restrictions on the size of the window that can be opened, thus limiting natural ventilation. The reason for that is that it becomes a risk of somebody falling out. And in fact, we actually had somebody in our locality, a child fall from a window in an apartment block recently. So the reason for keeping those windows secure is very important. But also security, people becoming more concerned by the risks of burglary and other matters. So in order to carry out the analyses, which could identify greater detail from the impacting issues, we instigated a parametric study in which a number of different key features of the building apartment was varied. We considered that the apartments would be ones in which they would be surrounded in all but one side. The side not surrounded is of course the one with the windows, the openings in it, but the other 5 sides of the building, the top, bottom, 2 sides and the back, would all be surrounded with temperatures at a similar level. We considered 1 and 2 bedroom apartments with typically 2 and 4 occupants. And we used the programs Energy Plus and Design Builder to carry out the simulations. And in total for this particular set of circumstances, we had 1,920 parameter combinations that were analysed. The building we chose was not an extravagant one, it's quite a typical one, about 12 stories in height. We considered apartments situated facing each of the 4 principal directions, north, south, east and west. And we considered apartments on 2 different floor levels, the 2nd floor level and then the top floor level. And typically we had a 12-story building for this. Now, one of the benefits of using an apartment block like this with multiple apartment options in it was actually in carrying out the simulations. We could carry out more than one simulation at a time by using different facades of the building and by using different floor levels. The reason why the 2nd floor was chosen is this represented an area where perhaps there was restricted ventilation because of surrounding buildings, and the top floor because it was more exposed to heat gain from the sun above. The basic parameters for the layout of the apartments were chosen from a number of sources where apartments were described and instigated and used in real buildings. And the 1-bedroom flat you can see on the left here with a window in the bedroom and a window in the combined dining, living, kitchen area. The apartment on the right, I'm sorry it's the other orientation, but you can see 2 bedrooms and also linked area with the combined kitchen, dining area and living area. I know that this would not be common in all parts of the world, but for the UK, this is quite a common set of circumstances. The different parameters that we looked at were 3 different city locations in the UK, London, Manchester and Newcastle, to give a breadth of different climate variations. Also looked at 2 variations in climate, the historic data from 1961 to 1990, and then the 2050 predicted data according to the 50 percentile high emission scenario. As I already said, 2 apartment types, 2 locations in the apartment block, and different window variations with open windows in different bedrooms and so on. We also had high lightweight and heavyweight construction variations and differences in leakage orientation and occupancy patterns. Heat gains were determined from glazing and internal gains from the people occupying the space. The TM standards for vulnerable occupants were set, and unfortunately we found that almost all the circumstances where that particular set of standards were used failed the test. Overheating risk, particularly in the 2050 scenario, with significant different discomforts like in the almost all situations for the future weather. 20% of ours indeed were uncomfortable, with the top floor apartments suffering the highest risk, typically 15% greater overheating or compared to the lower level. The high insulation lightweight building scenario increased the summer overheating even further. And overall, the highest temperatures was for the south-facing apartments. This was a little bit unusual because normally you would expect for the west-facing apartments. But in this particular circumstance, it's the south-facing. Excuse me. We used occupancy patterns typically used in existing assessments, but actually these were not adequate to allow for the increased occupancy due to COVID restrictions. So therefore we had to change those in order to determine what the impact might be. So there was an increase of internal heat gains both from the body heat of the occupants and also from the other effects of things that they were doing, increased cooking quite typically. There are several complexities in comparing the impacts of using these different assessment criteria from the technical memoranda. So the standard way we would be assessing overheating basically failed to address the particular problems we had with COVID, and this needs to be addressed in future development of the standards. We're also aware, of course, that we were only looking at 3 locations, but because they spanned from the north to the south of England, at least it gave us some ability to discriminate between what might be happening in slightly varying climate, but we do need to look at wider range in the future. The calculated temperature predictions did give us greater detail and therefore added value compared to the standard procedures. And I think we would really be recommending that the standard procedure is an addition is provided to cope with those kind of circumstances that we found ourselves in with COVID. And although the 3 locations, limited number, we did think we got an overall indication of performance. I think we would definitely suggest that the discomfort hours that we standardly work with in the normal ways of predicting these things are not sufficient, because the observations we made, and particularly during daytime for occupancy of apartments, was not sufficient to allow us to estimate the overall problems. And if we're looking at the wider scenario in which potentially death and morbidity can increase as a result of higher temperatures, then we do need to enhance our way of understanding this particular problem. The use of thermal insulation also had an overall negative impact. And this is a bit of a problem in the UK, given that at the moment we are attempting to improve our insulation standards. We need to be careful that in doing that, we don't create more problems than would otherwise be the case. So there needs to be more concern paid to technical detailing. So we need more in-depth analysis, and we're partly doing that already, have a research student dealing with this, further ongoing work. We need to do some testing of real-world examples. Unfortunately, because of COVID, we were not able to measure in real buildings at the time of this parametric study, although we were using standard methodologies of simulation. But I think we do need to expand into testing of real-world examples. And particularly, we need to align the analysis to the development of new codes for overheating, which is going on in the UK and elsewhere at the moment, and more sophisticated measures of assessing overheating risk, so that we can consider the particular circumstances, not just of COVID, but there are other factors which might impact on the way in which we're using the buildings. Certainly, we can see the impact of orientation is complicated due to specific weather patterns and building parameters, and the matching of weather data to the analysis needed, particularly in terms of ventilation. That's quite difficult to incorporate into the way in which the analysis moved forward. We could see from the way in which we had to put together a particular input data that needs more help. And I think I've more or less run out of time. So I think I'll say thank you to everyone for listening. And if you have any questions, please do ask me, and I'll pause the sharing here.
Thank you very much, Professor Pitts. I think we will go to the next presentation, and I argue that the attendees or any panelist, if they would like to ask question, you can post it in the chat box, please. So our next speaker is going to be Professor Eleni. Please, you can share the screen and introduce yourself to the audience. And you have 15 minutes.
Yeah.
Thank you.
I suppose you can see my screen. Can you see my screen, please?
Yes.
Yeah.
Yeah.
Okay. Yes. I'm Dr. Elaine Tracada. I'm a senior lecturer at the University of Derby, and I teach in architecture in the built environment from, let's say, level 1 to PhD students. In fact, I've got also one of my PhD students attending, as I can see from the participants. Anyway, my theme, as you say, is getting cities taking immediate climate action to protect buildings and blue-green infrastructure. And our plan is also, as we have started doing research for some time now, to suggest to our local council, in Derby City Council, that they should allow time to do voluntary review plans. We started working on different matrices, and what I'm going to present here, it is, if I can go to slideshow, it is about city of Derby to becoming a livable city. They started thinking about being a smart and livable city, but what we really see, it is the conditions that we can have with extreme climate nowadays, which was not considered some time ago, probably in the master planning. Now it is something that we consider, although the city is in the middle of green areas, etc. It has a river and at times suffers from dangers of floods, and frequently, lately, I can say there has been real risks about the health of the people and citizens because of the lockdowns and not having an infrastructure, especially green and blue infrastructure, to be used at all times. So we started doing some research for some time, and we are promoting at this case to become Derby a daring city, promoting the 2030 Sustainable Development Goals of UN. But in our studies, we have started considering all these particular schemes and targets according to what is going to happen if we need to do a bit more work on the blue-green infrastructure, and especially in all urban spaces, as we can say. But we started with modules and undergraduate level. Now we're expanding to master's degree with health in buildings and the built environment. And we deal also in postgraduate studies looking at architectural buildings, but also to the urban space as well. And the SDGs, we leave to students also as they do their research with us, sharing the research about the city, to see what priorities should be and what the indicators are, which come across things that we look at synergies between us as academics, but also as citizens of the same city, find out indicators according to the territorial approaches that OECD program for daring cities has put up. And we've participated in several of these roundtables to learn about these methods. Now, the students also create proposals or solutions which are considered and discussed with little forums of citizens or in surveys. Although last year we had a problem with face-to-face surveys, some students attempted, because it's urban space, to do in open space discussions with citizens and promote several things which they have considered in their projects, getting feedback again from the citizens themselves. And we are going also to organize a full exhibition and discussion pretty soon in I think at the beginning of next year to audiences. Probably if we have also the campus available to invite people from the communities and also the council and disseminate our findings. We have been based, and the projects have been based upon an index which is called Biophilic Healing Index, promoted like a concept by Professor Nikos Salingaros, who is a scholar analyzing the work by Christopher Alexander on patterns. And we worked together closely with Professor Salingaros. We found out that 10 at least of the so-called patterns of nature can be used in urban space and buildings. Probably we started with buildings, and then we are promoting the same thing in urban space. And the main things that we are considering is sunlight, color, gravity, is balance, especially of people, considering the vertical axiality of the buildings, fractals, which things occurring on nested scales, so a continuity in different spaces and places without barriers, curves on small, medium, large style scales, detail to attract the eyesight, but also the other senses, as I promote in urban space, water, heard and seen, life, living plants, animals, and other people. Then representation, nature, realistic paintings, reliefs, figurative sculpture, anything that has to connect you with nature. And finally, organized complexity, which means intricate and coherent designs. Now, if we do that with people, we ask people really to give us a value on what they see in their building or maybe in the space, in the streetscape, between 0, 1, and 2. And then the biophilic index, it gives us a percentage multiplied by 5. So if we get, let's say, sunlight that gets 1, as you see here, is multiplied by 5, and then we get a summative of all these things, like the student did about the project for the main central area of Derby. You can see the first things that we were getting from these values were no more than, for the existing, were no more than 30% of the total value of 100% of biophilia. Then students considered and also showcased with photo elicitation to people different ideas of their project to add up sunlight in the main piazza, as you see, fractals, which means flow without barriers, and so on, and managed to get 70% of 100%. It's a very difficult area, though, because to go to 80 or 90%, we have also to consider that the surrounding traffic has to be completely dismantled. So these are ideas that the student put for the central marketplace and the central part of Derby. Co-working spaces to give people more life there, because it was a lifeless place most of the times. And as you see underneath, they're promoting also different things about the sustainable development goals that the council should put in place in the new master plan that they are going to be implementing, and they won't change up to 2030. Especially work has been done for students on revamping different things of nature that have been underneath Derby, and those works took place after World War II practically, and just before, like revamping brooks and nice walks in the city, so making the city more walkable. You can see that along the river, the existing situation is not a safe place, especially in the evenings and even in the day, because there are several things that they are not attracting people, and they are not also usable by people, these path alleys. So the students added more life, more green space, also gardens that they create a sponge city environment just in case that we have an overflow river. Then there are again different views, as you can see, the existing and how it is completely transformed with green infrastructure, blue infrastructure, and also the consideration that students did with colleagues from biodiversity is to extend the greenway so biodiversity in the city is not disrupted, because we've got biodiversity at the edges towards the Derbyshire Dales, but not inside. Then this student did a lot of more work looking at a green park, which is a beautiful park if it is revamped in a way that people can see that as an urban biophilic space. So he did a lot of research there, helped with another couple of students, and looking at the opinions of the people, using the biophilic index as well to indicate different things about this green park, which is a big, huge park, not very far from the green space, from the central part of Derby. It should have been a great idea for especially people working also in Derby to enjoy different things there. So the final plan that you can see there provides also a boat, like a small bus boat, let's say, to take people from the central part of Derby to that park and use it in various things. These are ideas also promoting green along the streets and promoting streets that they can be walkable and can also integrate transport, which gives you the famous 50 walkable cities nowadays. And again, revamping all the streets to bring back all the green space and blue space that is being lost, but in a way that creates communication through the city and creates itineraries either for citizens and the people who live there. There are more views of cities, and if you visit these streets now, they are not having anything very attractive unless the environment is going to be changing. So the promotion also is, as I said, evidenced in mapping on where these priorities should be, like creating another layer of master plan by showing priorities. Zones that they are in danger of having floods, they've been also mapped from students and staff, and we are now promoting things that they create a green space to be saving city. But in the meantime, people who would like to see these things because they feel extremely stressed and stretched with what they have faced, especially with the latest lockdowns. And these are areas also nearby the university, which is practically cut off by a main street road, the A38, a very busy road. And now the heritage and also the highways are planning to do that stretch underground, or maybe do a smaller channel underground just for the service of the city and deviate all the traffic in other ways, and giving the space on the top to be communicating between also another green park of that. So I stop here. We are doing research with the Biophilic Index, and we are planning to do validate this tool, like a framework tool, for planning, but also extending to the built environment itself, because we think that biophilia should be a combination between indoor space and outdoors together to be working for the citizens of the cities. So I shall stop here, and thank you for your attention.
Thank you, Professor Eleni. Please, if you have questions, I can see some questions, post them on the chat box so that we can take them in the Q&A session.
Yes.
Yeah. So we have now Haytham Raspi, who's going to present the energy modeling of traditional and contemporary mosque buildings in Oman.
Yes.
So,
Assalamu alaikum.
Alaikum assalam. You have 15 minutes. Please go ahead.
Inshallah. Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. My name is Haytham Raspi. Today I'm going to present our paper, Energy Modeling of Traditional and Contemporary Mosque Buildings in Oman. I'm a PhD student in University of Nottingham, not far from Derby, where Dr. Eleni is just from. Okay, so this paper was just published in July 2021. The aim of this research is to investigate the thermal performance in mosque buildings in Oman. What we do in this research, we compared between a traditional mosque and a contemporary mosque, both taken as case studies. The objective is to understand the thermal building performance in Oman and its relation to vernacular architecture, and also to compare between traditional and contemporary mosque buildings thermal performance. Why we chose mosques? We chose mosque as a case study here in Oman because mosques are a very simple plan and simple layout, very typical across all mosques. So it makes comparison a little bit easier between them. And also for mosque, it's easy access. It has easy access to mosques. We can access them very easily. So for research is also easier. The research methodology we used was software ADSL TAS. This software was very straightforward and also powerful, and it suited our needs for this research. So we studied two mosques, Hudayfa bin Yaman Mosque in Muscat. It was built in 2015. And Al-Wafi Mosque, which is around 400 years old mosque. Those are two mosques we studied and we compared between them. Those are the drawings of Hudayfa Mosque, the newly built mosque, and the 3D model generated in TAS, ADSL TAS software. This is the Al-Wafi Mosque drawing and the 3D model of Al-Wafi Mosque. You can notice that one of the differences is the roof. For Hudayfa Mosque, you have a dome or a qubba roof, but for Al-Wafi, it has like a curved or cylindrical shape roof. Also, another difference between the two mosques, one notable difference is the construction detail. Most notably is the first line. If you can pay attention to the first line of each table, is the external wall. In the newly built mosque, Hudayfa Mosque, it's built out of concrete bricks, and for Al-Wafi Mosque, it's built out of clay or mud wall, or what we call in Arabic sarouj or tin. Also, because of the different material, there's a difference in thickness. In Al-Wafi Mosque case, it can reach up to 1.2 meters thickness. And of course, the U value, the specific heat, and the time constant are all different between the two materials. So as for the results, what we came up with, we have here the two charts. On the left, we have the dry bulb temperature. The blue line is the external temperature generated in the software, and the green and yellow lines are the internal dry bulb temperatures between the two mosques. There's not much difference in winter, but in summer, the Hudayfa Mosque, which is the right chart, it recovers a little bit faster, which means that the Wafi retains the lower temperature better, which means the Wafi Mosque has a better thermal performance when it's in a natural ventilated mode. We also looked at the loads breakdown. So I want to go into much detail. I just want to highlight here that there are many loads or thermal loads that we studied, and we looked at the most or highest loads that are affecting the two mosques. So for those two charts during winter for Al-Wafi Mosque and for the most notable thermal loads are the solar gain and also the external opaque conduction. And for during summer, the most notable thermal loads are sensible load and also external opaque conduction. And for Hudayfa Mosque, it's similar to Al-Wafi as well. It's solar gain and external opaque conduction. As you can see by the amber line, it's the solar gain, and the green line is the external opaque conduction. Also for Hudayfa Mosque, also during summer, similar to Al-Wafi as well, the most notable or highest thermal loads that we saw according to the simulation are the sensible load and the external opaque conduction. So in summary, for both mosques, what we noticed that the solar gain, external opaque conduction, building heat transfer, and sensible gain are the highest thermal loads that we saw. And also according to this simulation and according to previous literature as well, what potential improvement what we can do, as you can see on the right, is we can modify the glazing ratio, and we can modify the building envelope, for example, the VU value, or change the material of the building envelope, the walls and the roof. And also what we can do, we can change or increase the thermostat set point. So what we did after that, what we did the simulation again for both mosques, Hudayfa and Al-Wafi Mosque. So we did it 7 more times for Hudayfa. Each time we change something, we improve the building or change it. For example, at the left, the table at the left, Hudayfa Mosque, the first case, we halved the glazing ratio. We had half of the area for the glazing ratio, and then we doubled the glazing ratio for the second case. For the third case, we reduced the U value from 0.8 watts per meter squared Celsius to 0.4. And then the fourth case, we reduced also the U value for the external walls. Fifth case, what we did for Hudayfa Mosque, we exchanged the material. Instead of concrete, we kept it at mud wall. And for the sixth case and the seventh case, we increased the thermostat set point by 1 and 2 Celsius. Same cases we did for Al-Wafi as well. So what we noticed here is that the change in cooling load, the most reductions yielded by third case and seventh case in Hudayfa Mosque, which are reducing the U value. And for Al-Wafi Mosque, it was mostly reduced by thermostat set point increase by 1 or 2 Celsius. So in summary, as per the results, the roof's U value reduction and the thermostat set point increase by 1 or 2 yielded the most cooling load savings. It yielded up to 9%. Of course, we can mix and match between those techniques. For example, if we did both reducing the U value of the roof and also increasing the thermostat set point by 1 or 2, it will yield maybe up to 14%. and also another result that we came up with, the traditional mosque performed better in natural ventilation mode. The contemporary mosque consumed less cooling load than the traditional mosque as well. So that's all. That's it for us. If you have any questions, please let me know.
Thank you very much, Haitham, for the nice presentation. I'd like to remind the attendees and also panelists to post their questions on the chat box. So the last one on our session here is Professor Aouni is going to present improving pedestrians' thermal comfort in public urban spaces in Muscat City. So please, Professor Aouni, you can introduce yourself, and you have 15 minutes to present your work. Thank you. Professor Aouni, you are muted. Can you unmute yourself? Yes, you are okay now.
Yeah, thank you. You hear me now?
Yes, yes.
Good.
You can just be in a slight mood.
I'm a retired professor from Sultan Qaboos University this year. I have a Bachelor of Architecture from Liverpool University, MSc from California, and PhD from Texas A&M. My research interest is building environment and green architecture. So I'm starting my presentation to improve pedestrian thermal comfort in public urban spaces in Muscat City. Dr. Saleh, would you remind me halfway through, so I won't exceed my time? Okay. Do you hear me?
Yes, yes.
Yeah, okay. Well, I see the climatic environment as a very important factor in identifying Oman traditional architecture. Building relate to that, but on the other hand, the contemporary urban fabric is separate, scattered building with wide spaces, and the urban space lost its original role of people realm to automobile realm. So hopefully this research explores ways to improve the urban space pedestrian comfort against the challenge of the local climate. The urban spaces were theoretically simplified into abstract volumes made of floors surrounding by walls that represent the facade of surrounding building. Three elements were explored to restore thermal comfort. They are shading, wind, and landscape. The shading efficiency was calculated and used to compare urban spaces. Observations were made on cooling effect of prevailing wind, and the landscape was also studied. Field survey was conducted on selected sample of urban spaces in Muscat and ended up with design guidelines. The climate of Muscat, as you see here, actually, it has a very long overheated period from April to October and only very short comfort period. This difficult climate has limitation on pedestrian activities in outdoor spaces, and I found out that pedestrian comfort cannot be attained without shading of the urban spaces. According to the first note, I kind of classified urban spaces into four typologies: fully enclosed urban space, partially enclosed urban space, streets, and sea corniche. As I said, the three items were presented as a theoretical basis the effect of shading. I put the geometric configuration of an urban space was described by proportions of height to width and length, and I classified them into two types: deep urban space where height is greater than width and length, shallow urban space where height is less than half the width and length. Then shading efficiency was calculated and shading patterns were plotted. And one of the initial problems I found that due to the high solar altitude in Muscat, it causes low shading efficiency for vertical element and high for canopies, horizontal elements. So it is necessary always, especially in shallow spaces, that we must have supplementary shading support by canopies. The wind, as far as the wind is concerned, basically the surrounding building must be planned in a way to create positive and negative pressure to maximize wind flow. And then improvement of wind flow must be achieved by inserting gaps in a prescribed allocation between buildings. We have in Muscat the prevailing northeasterly wind. It is a very important character. It has a sea breeze cooling effect that reverses direction between day and night. And I look at Matrah neighborhood, old neighborhood, is a good example for exploring sea breeze. As far as the landscape, I classified landscape floors as hard surfaces and soft surfaces. And the relative proportion of these surfaces is given by hardness ratio, which is HR equal hard surfaces to soft surfaces. Obviously, hard surfaces absorb and store much of solar heating radiation, while green dissipate. But the problem is, it's very difficult to maintain green areas in Muscat due to high air temperature, intensive solar radiation, and mainly water scarcity. So although we wish to have green spaces, but we cannot have them. Therefore, a critical balance must be struck between both. The field survey was conducted on selected samples, and they were assessed on two issues: their level of sustainability, and to be compared in relation to thermal comfort using the following elements: shading, wind, and landscape. The samples, the first sample is SQ housing. It seems to be that the top of the slide is not shown, it's cut off somehow. And this sample, the concept of traditional oasis was revived, and the houses retreat from the desert and turn into introvert green cool environment. Shading efficiency of streets in the in the east-west axis are higher than north-south axis. The streets in the north-south axis facilitated the flow of wind currents, and contrary to the others. In the east-west streets, the trees, as you see here in the diagram here, the streets in the south pavement, the east-west street, the trees at the south pavement are effective in shading the street. On the other hand, the trees on the north side pavement do not present sufficient shading. The second sample, this is academic building space in Sultan Qaboos University. Here, the shading efficiency is low because the floor is large, surrounded by low buildings. The building at the east and west edges provide the highest floor shading efficiency, while the southern building provide low. The space includes a group of large trees, but they do not provide adequate shading because they are located in the north. Although the space is U-shaped, facing north, it does not facilitate prevailing wind flow because it does not have open gaps, as I said earlier. Therefore, the floor is a heat island because it's paved by concrete tile that absorbs solar radiation and radiate heat to the space. The results of the selected model can be discussed as follows: their level of sustainability and ability to respond to climate challenge. And the third is capability to provide pedestrian comfort by employing, again, the three elements. We conclude in the discussion that a few urban spaces in the sample of deep configuration, and they do get adequate shading, but the majority are shallow configuration and do not get sufficient shading. The effect of the surrounding building on the shading efficiency can be rated in the following descending order: east, west, south, southeast, southwest, northeast, northwest, and north. The shading effect of eastern and western blocks surrounding the urban space are maximum at the morning and the afternoon, and minimum at noon. The southern building blocks, on the other hand, provide continuous but rather low shading throughout the day. Shading efficiencies in highest urban spaces with elongation to the north-south axis highest, and lowest when elongation in the east-west axis. The high solar altitude angle in Muscat causes canopy to provide higher shading efficiency than walls. Therefore, buildings surrounding shallow urban spaces cannot provide sufficient shading, and it is necessary to provide supplementary shading by trees and tents. As far as the wind benefit, I found that fully enclosed urban spaces suffered from air stagnation and loss of cooling effect. Semi-enclosed urban spaces in U form allow wind flow. Building around some urban spaces have inlet and outlet gap that created positive and negative pressure that induced wind currents to the middle of the space. Also, groups of trees were placed at the edges of some of the urban spaces to redirect. Yes.
You have 3 minutes.
Okay, fine. As far as the landscape, only few urban spaces sample contain small manageable gardens, plants that tolerate solar heat gain. But most of the spaces are shallow type and contain large garden that cannot be maintained. And another problem, some spaces have large grass turf, and that's also difficult to maintain because it's the need of water. So this is the crucial point. Some spaces respond to the challenge of water scarcity by greater urban spaces. We have to do greater hard spaces. We have no choice. However, the hard spaces were shaded by trees to reduce solar impact. The types of hard spaces sample, we have the concrete tiles, which is not good, absorb much solar radiation. We have the cobblestone and gravel, absorb less heat because of the self-shading effect due to the gaps in between. It can be concluded that the urban spaces in Muscat may be classified into unsustainable shallow spaces and sustainable deep. The unsustainable urban spaces are mostly shallow with a proportion less than half the width length. Some contain large areas that were difficult to maintain. They are mostly closed urban spaces. The pedestrian activities were diminished, and a problem, even many urban spaces changed their role from people realm to automobile. Actually, some were turned into parking areas. On the other hand, the sustainable spaces all of these sustainable are deep with height greater than width to length, contain small, easily manageable green areas. They are semi-enclosed and they allow heat flow. The hard surfaces are more than green, but as I said, they have to do that, but they shade them. And we recommend the following. To improve urban spaces comfort condition and activate, we do the following. We get high shading efficiency is necessary. We cannot work without shading. And it's achieved by usually deep urban spaces elongated in the east-west axis. The building blocks on the south of the urban space should be higher than those east-west. Supplementary shading is absolutely necessary and must be provided by trees and tents. Gaps should be included between the surrounding building blocks in order to simulate the flow of sea breeze. Maximum benefit of sea breeze is attained by street running in the north-south or northeast-south axis and by urban usage. And the landscape, again, must be utilized to provide shading effect. And we must have small green spaces to accept the challenge of water. Hard surfaces has to be larger. We have no choice, but it must be shaded. Housing neighborhood could be could follow the traditional oasis by an introvert. Again, the COVID-19 pandemic has caused significant change in behavioral patterns, and there will be a shift from indoor air-conditioned public spaces to outdoor. Therefore, greater attention must be given to improve the outdoor pedestrian space environment and put a new standard. And thank you very much.
Thank you, Professor Awani. Professor Ahmed Taki, can you please handle the Q&A session? You are muted, Prof. Ahmed.
Thank you. Looking at the chat box, we've got a question from Rijal to Adrian Spitz. How did you model the window opening behavior? Did you validate the simulated results by the measured data? Have you done any energy saving analysis? Is Adrian there?
Yes, I'm here.
Oh, hi, Adrian.
Hello, nice to see you again, Ahmed.
Nice to see you.
Well, except you can't see me. And thanks, Hom, for the question. Yes, this was actually a tricky part of the analysis because the modeling of window behavior is one of those areas where the kind of information we needed wasn't truly available. What we assumed was when the temperature reached a certain level was that the occupants would open the window, and then we adjusted the ventilation rate accordingly. But of course, because we're in a real situation with some real measured weather data, we could look at the influence of the wind in the surroundings. But actually, it was one of those topics which we think more information, more detailed modeling would be needed. So we're sort of pleased and confident we could get some kind of output from it, but it could be done in a more sophisticated way in a future analysis. We didn't validate the results by comparison with measured data. I think I mentioned in the presentation, we were not being able as yet to create any measured data. So these are purely simulated data, although we have got quite a lot of experience in using the computer simulation software that was employed. And we haven't done the energy saving analysis. And I think actually it's one of those things in the UK which we need to look at, because recommendations from COVID are to have windows open much more frequently, and therefore there is going to be much greater heat loss, particularly in winter months. So I hope that's sufficient for Hom.
Okay, thank you. Thank you, Adrian. I've got a question to Eleni Strakada as well. I'm interested in how much emphasis was placed on the blue infrastructure as compared to the green, and the weighting ascribed to each, please. Is Eleni there?
Yes, I'm here. If I can, yes. Hi. Yeah, in the measurements we did. Sorry. Can you hear me?
Yes, sorry.
Okay,
there was one.
Sorry, because I was hearing some background noise.
Yeah.
Yeah, the infrastructure, the blue infrastructure, we took it in equal, let's say, measurements from what the people were also showing in response to the biophilic index measurements we did. But at the same time, as a team of research scholars together. We are working in a group of nature connectedness, and with another professor, Professor Miles Richardson, we are looking at how blue infrastructure could be an integral part of planning the green infrastructure in the city, because practically Derby is in the center of town. And we've got like case study or connections with our campuses to the center and the inhabitants in that area. Lacks that kind of connection. There is continuous interruption. Blue infrastructure has been disappearing from the center of town. So what we looked at the questionnaires and what was coming also from the research from Professor Richardson, it is that we have equally considered blue and green infrastructure in our proposals, or probably in what we think to do, like a review plan for the city. Although the city is now developing several developments in the center without any kind of introduction of these two elements in the context, the students are working, and especially at master's level and PhD level, to promote more to the point to focus mainly, as we said, to equally consider both green and blue infrastructure like a same thing, not separating, because it should be the case that the plan should be working properly for a walkable city as well.
Thank you, Alia. Thank you. I've got a question for, is it Ani Shaban? Which materials do you think are suitable for open spaces that can allow some trees to survive with extreme heat? And another part of the question, do you use rainwater storage under hard surfaces, at least in case of freak rainstorms? Or do you suggest use of grey waters for I can't see the rest of the question.
For landscaping.
Landscape, yeah. Over to you, Professor Shaban.
Prof. Auni, can you unmute yourself?
Yeah, do you hear me?
Yes.
Yeah.
Okay. Well, first of all, you see, we must very quickly look at Muscat compared with London, for example. London, you could have a lot of green, there is a lot of rain, no problem. Here, we don't have a lot of rain, the weather is very hot, water is very little water, so we have no choice but making hard surfaces larger than green surfaces if we expect them to continue on making. Now, the problem is, you know, and we all know, hard surfaces are not very good because they absorb heat. So the solution to it is shading it by trees, spots of trees. With the material of the hard surfaces, the standard is the paving tiles, which are not very good at all. They absorb a lot of heat. We have experimented with alternative, which are cobblestones. And you see cobblestones next to each other create shade, mutual shade, and they absorb much less heat. Now, as far as water, yes, we extensively use treated gray water for landscape irrigation. Thank you.
Thank you. So another question for you. Thank you. That's again from Rijal. Thank you for a nice presentation. How did you define the monthly comfort and overheated periods? Which standard did you use for analysis?
Is that for me?
Yeah.
Okay. The table on the top first presentation gave summary of the calculation and analysis of the climate, and that is, we used a bioclimatic chart. We've loaded the temperature and relative humidity, and we have comfort limits on that between 21 and 26 or 25. So anything above that is the overheated period, and anything below that is underheated. As you notice, we don't have underheated. There is no cold weather. There is comfort, very short few months. Thank you.
Thank you. There is a question from Suruf. Is there much work? I think it's to you as well, Professor Shaban. Is there much work on the reuse of grey water from baths, showers, and sinks to water planting in outdoor spaces?
Just will you repeat the last bit of the question?
Yeah. Is there much work on the reuse of grey water from baths, showers, and sinks to water planting in outdoor spaces? It seems like a vital piece of the outdoor comfort jigsaw. And the other part of the question says, have you tried earth surfaces like they use in many French and Spanish settlements?
Okay, the first question, yeah, we use gray water, not black water, and one of the research work are actually done in our Sultan Qaboos University Eco House, which I'm the project leader. So one main issue is water saving and treated water used for the irrigation. Actually, there are many places in Oman in which treated water is being used. Now, the second question I didn't understand. Using the French.
Yeah, have you tried earth surfaces like they use in many French and Spanish settlements?
Yeah, but what are these they use in many?
Yeah,
let
me invite Sue. Sue would like to elaborate on your question.
Yeah, Prof. So, what are the samples you're saying in France or in Spain? What do you mean by?
I think Professor Su is saying that if you would like to know more about this, there are some presentations in the next few sessions that talks about this.
Yeah.
Yeah.
Okay.
I have a question to Professor Pitts. I think we are done with the attendees, right?
Yeah, I think that concludes all the questions in the box. Go ahead.
I have my own questions.
Yeah.
I would like to take the opportunity. First of all, we always talk about the future scenarios for climate change, taking into consideration the climate, the outside climate as boundary condition to our simulations. My question to Professor Pitts is there any future scenarios for internal heat gain? We know that people are, in fact, you know, the heat coming from people is not much, but the use of equipments, new equipments, is there any kind of scenarios for those?
I'm not aware of any that have been set out yet. In the research we do, we often make some assumptions about some of those changes. For instance, we recently did some work in Vietnam, which is a warm country, although more humid than, for instance, Oman. And in that country, we were considering the change of appliances, where different appliances have different energy use, and therefore the heat gain that comes from that you have to adjust. And there is a little bit of work on the input from humans, but we haven't really investigated that in much detail at the moment. So it's mainly been from the additional appliances and the use of those appliances and the change in uses of those appliances over a period of time that we've tried to look at. But as I said, that was mainly in relation to a project in Vietnam that we were looking at.
Okay, thank you. The question then is to Dr. Eleni. Eleni, is regarding the project, whether it's been completed. If it has been completed, is there any post-analysis after the redesign?
No, it's not completed yet, because now we are trying really to validate the tool against the master planning. So we need to have the reaction also of the planners and the town planners, but we need also the reaction from the citizens to tell us if they feel comfortable with this environment. So the university is preparing also a virtual reality model in which all these things should be inserted. And we call this model DUST, the Derby Urban Space Transformation, anyway. And we include the coming built environment in the future because there's new progress on new buildings, etc. And we shall try to input with our postgraduates together this information and deal with the model anyway. So it will take us about a year. They have to finish off all the model and then showcase it like a proper tool for cities.
Thank you very much. I have a question to Haytham Rasbi. Regarding the comparison, you have compared two different mosques in two different climates. Haytham, are you around?
Yes. Yes. Yes, compared the two mosques in two different times.
Why you didn't select a modern mosque close to the old mosque, the vernacular compared to the modern in the same climate?
What we did in the computer simulation, we assumed the same climate. So we used the same climate for both, actually, for the computer simulation. That's something that we did. So actually the climates that in reality they're a little bit different, but what we used in the simulation is Muscat climate only because we found the file that we found it for Muscat more comprehensive.
Okay, thank you very much.
Thank you.
Prof. Ahmed Taki, do you want to end the session?
Yeah, just a couple of comments I'd like to make. I would be interested to know the environment and the contextual conditions that lead to overheating and heat stress in buildings, and that how would that be correlated or differ from the perception of individuals and comfort or discomfort. This is one comment. Also, when we do simulate buildings, I think we need to ensure like to like. For example, especially in mosques, what about occupancy pattern in typical Jumu'ah prayer, and what's the impact on people's perception inside the building, rather than just producing predicted results from a dynamic thermal simulation model. So those are two comments. If someone would like to add to this or to elaborate on this.
Yes, you're right. That's very correct. For the simulation that I did, actually I input all the internal conditions and the occupancy pattern as well. We considered that for Jumu'ah prayer, it's a little bit different because it's once a week. The occupancy is a little bit different. So that particular situation we didn't consider, but we considered that the mosque has like intermittent occupancy. So it's occupied 5 times a day. That's something that we considered in the end.
Okay. Yeah. Okay. I think is that it, Salih? I think we'd like to thank all our 4 speakers and the audiences as well. And would like to conclude this session, and it's time for a break. Thank you very much.
Thank you so much. Thank you.
Thanks.
Bye.
Bye.
Thank you.
Bye.